there are some integrals that simply cannot be done with any of the techniques that have been covered previously in this course. Integration by substitution and integration by parts, trigonometric substitution, all of these and more give us a very broad ability to handle a wide array of integrands, but there are some that are simply too complicated that it might be possible for these techniques to eventually work, but the time and energy it would take to go through them is ultimately just too much. There are others that simply no algebraic technique is going to work for. In these cases, we have to return to basics. Whether it was limits or derivatives or integration, the first form of all of these was to do them numerically. We then eventually moved on to algebraic techniques because we found that the algebraic techniques were more efficient when they were applicable. There are some integrands that there is just no way for the algebra to work, and so we have to return to the numerical approach. The numerical approach means that we use a finite number of subintervals, and we actually calculate something on each of those subintervals. In Calculus 1, when you first learn integration, you learn about the left, right, and midpoint Riemann sums. Each of these uses a rectangle drawn on each subinterval to estimate the area under the curve. Now, we chose rectangles at the time because they are the simplest area formula to calculate. And if we have to calculate numerically, then we want to keep that as simple as possible. As it turned out, using a rectangle, the simplest of all area formulas, also resulted in the simplest integrand for when we eventually learned algebraic techniques. Now, there were three schools of thought for how to use each of these. Let's look at a function on an interval from a to b, a continuous function, of course, if we're integrating. That would then be divided into, just for the sake of ease here, we'll use 4 subintervals. So that a would now become known as x sub 0, and then we would have x sub 1, x sub 2, x sub 3, and b would be known as x sub 4. To do a left endpoint Riemann sum would mean that we draw a rectangle with its base along the x-axis, and we use the height of the rectangle, or we determine the height of the rectangle by the y value of the function at the left endpoint of the subinterval. Now, this will, depending on the steepness of the function, depending on whether it is increasing or decreasing, and depending on whether it is concave up or concave down, this may result in either an overestimation of the area or an underestimation of the area. In this case, this left endpoint rectangle resulted in an overestimation of the area of this region, because it includes a section in the upper right that is not actually part of the region in question. However, we will see that as we look at other parts of this curve on other subintervals, we will find that at times the left endpoint technique results in a underestimation. On the second subinterval, we are going to again use the height of the function, the y value of the function, at the left endpoint of this subinterval. And again, we get an overestimation, although this time not quite as much. And then we repeat this on each of the further subintervals. And on the last subinterval, we finally get a chance to see where the rectangle is underestimating the true region. Now, this does not necessarily provide the most accurate estimation because it does. Every rectangle is naturally going to either be overestimating or underestimating. In very rare circumstances, we might find that it does kind of have a mix of both, but that is incredibly rare. Most times, each rectangle will either overestimate or underestimate. Now, another alternative, of course, was to use the right endpoint. The right endpoint would base the height of the rectangle off of the y value of the function at the right side of the subinterval. Now, again, we're going to see a similar thing to what we saw in the left endpoint, that some of these rectangles may underestimate and some may overestimate. On the second subinterval, we again use the height of the rectangle based on the y value at the right endpoint of that subinterval. And again. And again. This is going to ultimately give us a very large underestimation of the area. The only rectangle that would give an overestimation is the last rectangle on the last subinterval. So we actually get kind of the opposite effect of the left endpoint. When the left endpoint rectangle would overestimate, the right endpoint rectangle would tend to underestimate, and vice versa. Again, there are very rare circumstances where we may find that the left and right endpoint rectangles kind of balance out. But for the most part, one of them will overestimate while the other underestimates. And then we have the midpoint. The midpoint is the most involved, but also will turn out to be the most accurate. The idea of the midpoint rule is that rather than use the left or right endpoints, we calculate the midpoint of each interval, and we base our rectangle off of the y value at the midpoint of the interval. The idea here is that by using not the left side, which in this particular case overestimated, and not the right side, which underestimated, we instead strike a balance between them. If one of them is always going to overestimate and the other is always going to underestimate, then the midpoint is going to strike a balance between them by excluding some area that should be there and including some extra area that should not, thus striking a bit of a balance. It's still not a perfect balance, but it is a balance. Continuing on then, we would find that the second rectangle would appear like this. The third rectangle would appear thusly. And the fourth rectangle like so. Each one of these rectangles on its subinterval is a better estimate than either the left or the right endpoint itself. Now, in terms of the formulas, they appear very different. The left endpoint Riemann sum would be based on the height of the rectangle at the left subinterval, the left endpoint of the subinterval, whereas the right endpoint Riemann sum would be based on the y values of the functions at the right endpoint of each subinterval, And then there's the midpoint rule, which formulaically is going to look much more complicated. Because in order to calculate the midpoint, we have to take the left and right endpoint of each subinterval, add them, and divide by 2. And admittedly, this is going to look far worse. But in practice, this actually isn't nearly as bad as it seems. This is why when we did it algebraically, we tended to avoid the midpoint rule. Because algebraically speaking, this would be a nightmare. However, numerically speaking, this is not nearly so bad. It's actually not really any more complicated than the left or the right endpoint. And that's based on the fact that in each of these, we are using a consistent width subinterval, which means that the x values we're interested in using, whether it's the left endpoints, the right endpoints, or the midpoints, even the midpoints are spaced by the same amount of spacing as the left and right endpoints themselves. So once we've established one midpoint, all we have to do is continue to add the value of delta x across. For this reason, since the midpoint rule is the most accurate numerically, it is going to be the best choice for numerical integration. Let's look at an example. We're going to look at f of x equals sine of x on the interval from 0 to pi. Now, this is a function that we can integrate easily enough because the antiderivative of this is quite simple. The antiderivative of sine of x is, of course, negative cosine of x. And we then have negative cosine of pi minus negative cosine of 0. Cosine of pi is negative 1, and cosine of 0 is positive 1. So we have the opposite of negative 1, which is 1, minus negative 1, which becomes plus 1, and we have an actual area of 2. Now, this value is useful to know because it can tell us whether our midpoint numerical method is giving us an accurate value or a somewhat accurate estimation, as it were. Now, to deal with this, let's first sketch the region. Always a good idea. So sine from 0 to pi is basically an arc. With that being said, what we're going to do first is look at this with 4 subintervals. So halfway in between, and then each of those is halfway. This results in a delta x of pi over 4. Now, if we were using the left and right endpoints, then we would simply be able to use these actual values. But if we're going to use the midpoint rule, then we need to find the midpoint of each of these subintervals, which actually isn't that hard. Again, once we know that delta x is equal to pi over 4 when we use 4 subintervals, then once we find the midpoint of the first subinterval, all we have to do is add pi over 4 repeatedly. the midpoint of the first subinterval should be pretty easy to find, halfway between 0 and pi over 4. That would be pi over 8. And if we add pi over 4, well, we could think of pi over 4 as 2 pi over 8. Adding 2 pi over 8 would get us to 3 pi over 8. And then 5 pi over 8. And then 7 pi over 8. And each rectangle then would be based on the height, the y value at the midpoint. Now, visually, this is what it looks like, but what's ultimately important is the red values along the x-axis, because those are the places where we're going to evaluate the function. So, the midpoint rule using n equals 4 would look like this. That the area is approximately given by f of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8 plus f of 7 pi over 8. And all of that times delta x, which we know to be pi over 4. So this would be sine of pi over 8 plus sine of 3 pi over 8 plus sine of 5 pi over 8 plus sine of 7 pi over 8. Now, admittedly, this is not the nicest thing in the world because none of these are nice angles, common angles from the unit circle. So we have no choice but to turn to the calculator. Now, that being said, there are ways to deal with some non-common angles from the unit circle. Like pi over 8 can be done using the half angle formula. However, that seems like a bit of unnecessary work to get an exact value when the whole point of this is to do it numerically. And if you recall from doing numerical limits, the exact values are not the best way to go about them. The decimal equivalent is actually the best way. So we're going to end up putting this in the calculator. Now, that being said, if we're going to put it in the calculator, we can put it in like this. And because there's only 4 subintervals, that's totally reasonable to do. However, if we were to have 8 or 16 or 100 subintervals, then it would be nice to have a quicker way to put it into the calculator. And what we can realize here is that pi over 8 and 7 pi over 8 are actually symmetric to each other in the sense that they have the same y-coordinate. And since sine is the y-coordinate, an important thing to note here is that sine of pi over 8 is actually going to be equal to sine of 7 pi over 8. Likewise, 3 pi over 8 and 5 pi over 8 are symmetric in that they have the same y value. So what we could do is, instead of having to type in 4 of these things, what we could do is combine the sine of pi over 8 with the sine of 7 pi over 8 and write that as 2 times the sine of pi over 8. Likewise, we can combine the sine of 3 pi over 8 with the sine of 5 pi over 8, since they are the same value, and call it 2 times the sine of 3 pi over 8. And this would give us a simpler expression to put in the calculator. We could, if we chose, then factor out the common 2. We could combine or simplify that with the pi over 4. We could take further steps, but the idea here is that eventually, no matter what we do, we're going to have to put this into the calculator and evaluate it. So the extent to which we choose to simplify this is really just a matter of choice. But ultimately, when we're done with all of this, we get an area estimate that is equal to 2.052344, etc., which is fairly close to the actual area of 2. Not bad at all, actually. Now, that being said, in the nature of a limit, we would then want to increase the number of rectangles, because the idea is the more rectangles we use, the more accurate our estimate is going to be. So we're going to take this one step further, and we're going to do the midpoint rule with n equals 8. Definitely more intervals, definitely going to be a bit more work, but still reasonable to work with. Now, I'm not going to draw the picture on this because the picture does eventually start to get a little bit ridiculous. However, we start with delta x being pi minus 0, that's the width of the full interval, divided into 8 equal sized pieces, and that gives us pi over 8. Now again, all we need is the first midpoint, really. So we're going to start with the first subinterval. And the way to get the midpoint of that, of course, is to add the two endpoints and then divide by 2. And this will end up giving us pi over 16. So that's the midpoint of the first interval. Each other subinterval is going to have a midpoint that is spaced out by pi over 8. So our midpoints then are going to be pi over 16, and then 3 pi over 16, and then 5 pi over 16, etc., up to 15 pi over 16. These are our midpoints. So our approximated area will be given by sine of pi over 16 plus sine of 3 pi over 16 plus sine of 5 pi over 16, etc. So that we have 16 such terms. And at the end, it will be multiplied by our delta x, which is pi over 8. Now again, if you realize that there is some symmetry here, you can simplify this by combining some of these terms. For example, pi over 16 is symmetric to 15 pi over 16. So those two sign values are going to be equal to each other. Likewise, 3 pi over 16 is symmetric to 13 pi over 16. 5 pi over 16 is symmetric to 11 pi over 16. and 7 pi over 16 is symmetric to 9 pi over 16. So if it helps, you can simplify this a bit, or you can simply put it in your calculator as is. And what we get here, after putting this in our calculator, is going to be 2.012909, etc., which is certainly closer than the previous estimate. So the actual area we know to be 2, and what we saw here is that with n equals 4, we got an approximate area of about 2.05. And with 8 rectangles, we get an approximate area of 2.01. Both very good estimates, both very close to the actual area with a relatively small number of rectangles. Now, as it turns out, there are other methods which, without making the calculation much more difficult at all, in fact, with really not making it with only the slightest additional amount of difficulty in the calculation, will produce even more accurate results. We will look at those in the next videos.